Okay, so anybody have any questions from yesterday? That what we did, the 4 quantum numbers. We're a little bit ahead of schedule, but we're kind of combining some of these concepts together. Okay, so those quantum numbers come from the electron configuration. Okay, that's a good way to look at it. This is probably the central theme of not only the Bohr model configuration, then we get the quantum numbers from this. So if we were doing the configuration for scandium without the shortcut, okay, what would that be? Okay. Okay. So notice we've got how many protons for scandium? So if we add together all these exponents, what are we going to get? 3, 9, 11, 17, and 4. Okay, 21. So when we start writing these little blanks, the orbital diagrams, it's coming from the configuration. Because later on, we're just going to be worried about the last electrons. But what we want to do is show how we arrive at those numbers. So we put a blank here, and each one of these blanks can hold a maximum of 2 electrons. So one S, and an arrow up, and an arrow down. So we've done this one. Then we go 2S. Okay. Now, since the P block can hold 6, and each one of these blanks can hold 2, how many lines do we need? We need 3 of them. Okay? So we'll put the 3P here in the center, and it's always good practice until you're really good at this to follow the bus seat rule, which means here's your bus seats. You occupy each empty seat first, then you start pairing them up. Okay? Oh, yeah. I'll see if anybody is paying attention. Then we go 3S, 2. Then how many lines are we going to put next? And how many total in here? All 6, because we've already established that up here. And again, one of the things you could have done is start pairing these up already since it's full. But it's always just good practice until you're really good at this to pair them up first. Okay? 4S2. Then we need 5. Does anyone know why we're putting 5 horizontal blanks on here? Okay, because the D block has a potential to hold how many? 10. Okay, so each one of these horizontal lines can hold 2. So then 10 divided by 2 gives you 5. Okay, so we kind of ran out of space. Put 3D under here, and how many arrows? And each one of these arrows, okay, denotes 1 electron. Okay, so you add up all the arrows, you would get 21. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, and that's what we have for the element scandium. Okay, arrows is whether they're up or down pertains to the spin on there. If it's up, it's 1/2. If it's negative, or if it's down, it's negative 1/2. So what that means then, okay, we're going to go ahead and put in our 4 quantum numbers and our variables, N, L, M, M and S. Okay? These two, the N and the L, are the easiest to find. Because the only one we're concerned about is this block right here. Eventually, when we get further down the line, when we're doing some of these bigger elements, all you have to do is just where the last electrons fell into. And if we're really good, we would talk about it would be the valence electrons. But you got to be careful with this because that 3D1 is not a valence electron. Because if you were specific about that, remember, you got 4s2 way out here, and then you have that lone electron right here. Okay? But still, the slide rule makes that correction and says the 3D is right, it fills up after that 4s2. Okay. I went through that really quick. Is anybody confused by this? Yes?
The E.
Okay.
Why did you put E instead of
Well, I can put a 1 there. It's just when you have that line on here, then it's kind of like, might blend in with the curved line. That's nope, nope. Just showing where that electron is. Okay, so again, where this comes from, we put a box around here, just like what we did with this yesterday. Okay, so that's why we left that up here. Okay, so the N comes from the big number where that last electron fell into, and that is what? 3. Okay, here's the big number we're talking about, 3. Yes, we'll talk about that in just a moment. Okay, L is a given value, and we talked about that just briefly yesterday. There's this table 1 on page 108 that has, it says the letter, and it has L, which is 0, 1, 2, or 3. Those are the assigned values. Okay, so with that, is this yesterday's lecture we're watching? Okay. All right. So now, on page 108, what is the value for L? It's given. Because it says once you find this letter, you correctly answered it, it's what? L is 2, okay? Which means M equals a value of negative L to positive L without skipping over 0. So a way of looking at that is, notice, that's going to be a total of 5 numbers, 5 possible combinations. Because a negative 2 to a positive 2 is 5 numbers. How's that possible? Well, here is negative 2, negative 1, without skipping over 0, positive 1, and positive 2. So that last electron fell into which one of these? Negative 2. So that goes here, and it's oriented up. So what does that mean? 1/2 or negative 1/2? Positive 1/2. And it's, you can just do that, or if you want to put the plus sign there, that's fine too. I prefer you put the positive sign, but you don't have to. Yeah. Last one falls into. Okay, so and there again, you might be looking at this and thinking, I don't even know what question to ask. But to me, the more we go over these, the more apparent that it's going to be. Okay? So just by looking at this, yesterday we must have done, we did manganese yesterday. Okay? 1, 2, 3, 4, 5. So since that says 3D5, okay. Oh, P5. I was thinking 3D. Okay, sorry. We did chlorine then. We did chlorine. Okay? So, with that, maybe let's go ahead and pick another D block element. So something 26, 27, 28, or 29? 28. So we want to do nickel then. Okay? So some of these numbers are going to stay the same, but some of them will be a little different. Okay? So upon this, here's our 3D block. If we are going to do nickel now, and I-28, okay, everything up here is still the same until we get to this point. What column in the D block does nickel fall into? Okay, so that means there's going to be a total of 8 arrows in here. And this is where that bus seat rule is so important. Because if you start pairing them up, 1, 2, 3, 4, 5, 6, 7, 8. Do you think that's going to be right? It's okay for some of these to be empty. But it's not okay if there's more than 5. Okay? What we mean by that is let's follow that slide rule. Or excuse me, bus seat rule. Because you correctly said we need to put 8, right? Okay? So there's 1, 2, 3, 4, 5, 6, 7, 8. Okay? So we're concerned about this guy right here. So, what's true about this right here? Is N anything different? No, it is not. Okay? So N is still 3. The last electron fell in the D block, so according to the table of a given value for L on page 108, what value does L have? It's still 2. It comes from that table. Then, since this is still a value of 2, negative 2 to positive 2 gives us our value for M. Well, our values for M are established right here. So where did that last electron fall into? So the value for M is now what? It's now 0. And that last electron, is it pointing up or pointing down? It's pointing down. So therefore, this is no longer positive 1/2, but rather negative 1/2. Okay? Left outside. Is it a little more clear? Okay? Left middle? Okay? Right middle? And right outside. Okay? So now, let's go ahead and take a look at page 107. I think we read the principal quant. Yes.
Okay, so and you get that from which, like on the slide rule, the
Yes. Okay? Then, with this, that's telling us from page 108 on table 1 where you get your value for L. So if it fell in the D block, the value for L is 2. If it falls in the S block, the value is what? 0. Oh, I think you can remember that. So, in other words, how many different possibilities are there? 4, right? They go in increasing values, 0, 1, 2, 3, Yeah, I was thinking 4. Because I forgot to count 0. So 0, 1, 2, and 3. Okay? So in increasing order, which block is the smallest with only 2 columns? S. Then P, so that's 1. D is 2, and F is 3. So there's 14 columns in the F block, so that's why there's 3. So in my estimation, it's not a Herculean task to remember that. Okay? And that will just come with practice. You're going to do probably a lot of these that eventually this is going to be old news, and what we want you to think about is, do you remember 2 weeks ago I was struggling so bad with this, but now it makes sense. Okay. So, did we read about this on page 107 yesterday? The principal quantum number. If not, we're going to do it right now. Okay. On page 107, principal quantum number, symbolized by N, indicates the main energy level occupied by the electron. This is your main energy level occupied by that electron, so that's why N is 3. Okay? Values of N are positive integers, only 1, 2, 3, and so on, because N can be all the way up to 7. Why would that even be possible? How many periods are there? There's 7. So that's why N can be 1 through 7. Okay? As N increases, the electron's energy and average distance from the nucleus also increases. So, the information beyond that, we just want to know the principal quantum number from the main energy level is what N is. Okay? Then, angular momentum on page 107, it says, except at the first main energy level, orbitals of different shapes, known as sublevels, okay, exist for a given value of N. These are different subshells of the d orbital. So what that means is, what that's trying to explain is that table on the next page. Okay? L is a given variable, just like when you're doing proofs in geometry. Okay? Don't you start out with a given information? Angle, side angle, or side angle, side, and information like that. Yeah, you're doing your proofs. Okay? So that's kind of like the same concept. It's given information. Okay? So back up to the last line on page 107. It says the values of L allowed are 0 and all positive integers less than or equal to n minus 1. Okay? So what that means is, with the exception, if you put 1 in for n, 1 minus 1 gives you what? 0. And that's why on that table 108 it says L is 0. Okay? So that's where that, because I'm afraid if we read through all this information, you're going to get a better feel for this the more we just do examples of that. Just know that N comes from the big number, L comes from the orbital that it's associated with. Okay? The next heading, it says magnetic quantum number. Okay? So what it says, the magnetic quantum number, symbolized by M, indicates the orientation of the orbital around the nucleus. Values of M are whole numbers including 0. Okay? From negative L to positive L. So that's why we write this here. Whatever you establish the value of L is, you have to include 0. So if one falls in the F block, well then your values for M are going to be 7 different values, because it'll be negative 3, negative 2, negative 1, not skipping over what? 0, Okay, so there's our fourth value. Fifth one is positive 1. Okay, fifth one is positive 1. Sixth one is positive 2. And then our seventh one would be positive 3. Okay? Because an s orbital is spherical and is centered around the nucleus, it has only one possible orientation. Okay? So we're not too concerned about all these different orientations. We just want you to know that whatever L is, there's just different combinations without skipping over 0. Are we thinking, oh my, this is terrible? Making sense. Okay? Okay? And then finally, the easiest one to find, okay, the spin quantum number on page 110. It just says an electron in an orbital behaves in some ways like Earth spinning on axis. The electron exists in one of two possible spin states, which creates a magnetic field. To account for the magnetic properties of the electron, Theoretians, did I pronounce that right? Theoreticans? To account for the magnetic properties of the electron, theoreticans, that's what I thought. Theoreticians, that was right the first time. Theoreticians, okay, of the early 20th century created the spin quantum number. The spin quantum number only has two possible values, positive 1/2 or negative 1/2, which indicate the two fundamental spin states of an electron. An orbital can hold a maximum of 2 electrons, which must have opposite spin states. That's why on each one of these horizontal lines, you're only putting a possibility of 2, because they have to have opposite spin. They have the same charge. They should repel one another because it's 2 electrons, right? But if they have opposite spin, then they can kind of hang out together. Okay? That's because what happens when you're looking at matter in the quantum state, there's a lot of things that we just don't know that possibly don't make sense. 2 negative charges should repel one another, but if they have opposite spin, they can hang out with one another. Why? I really can't answer that. It's just the way the matter is arranged. So, do you think doing another example would be beneficial, or have you had enough for today? Okay, so I would suggest that you try to step outside of what you think your comfort zone would be. In other words, that's entirely up to yourself. Okay? European. Okay, now, rather than drawing all of this information out, we said just by knowing what block that element in, that's over half the battle that you need to face. Because you had picked your, I want to say it's 68, 63, okay? So element 63. Okay, so we've already established, okay, what block are we in? So we already know one of those quantum numbers right now. We know the value for L. It's 3. Did we just pull that number out of a hat, or how did you know that? 0 is S. Yeah, it's the biggest. Okay. So otherwise, if you were to look on page 108, it's going to say the value for an F block for L is 3. Okay? You can either accept that it comes from that table, or we just read through that material again, which I feel will probably confuse a lot of you. Just know that this comes from that given information. Okay? Then the next thing you can do to help yourself out is just by knowing what period is. Now you got to be careful when you look at the periodic table because, okay, according to your slide rule, where is the first F block? There is no such thing as 7F or 6F. Your slide rule tells you that. It's either 4F or 5F. Okay? So then looking at that, is europium in the 4F block or the 5F block? 4. So now we already know 2 of them. We got this half right already. So this is 4. Okay? Now, how many horizontal lines do we put for europium? 7. Did you just pull that number out of a hat, or? Because it's half of 14. The F block can hold a total of 14. Each one of these subshells can hold 2, or a maximum of 2. So that's why you have to put 7 of them. Okay? 1, 2, 3, 4, 5, 6, 7. So we want to make sure we put 4F down here. So M, remember, equals a value of negative L to positive L without skipping over 0. Yes?
So, like, if we were to do this on a test and we had to explain the work or whatever, like finish the work, we just put the 7 or
This here?
yeah.
Yes.
Or would we have to write all
You don't have to write all that out. That's why I said let's step outside of our comfort zone. And we said when we get better at these, you don't have to draw all that information out. We can just go right to the heart of the matter and where these last electrons fell into these orbitals. Okay? Then the next thing we need to do is be able to count over, okay, what column in the F block is europium in. You got to be careful when you which periodic table you're looking at, because this is not part of the F block. It's part of the D block. That's up here. Okay? So 1, 2, 3, 4, 5, 6. Okay. So 6. Okay? All right? Yeah. Okay? So, upon doing that, remember, here's your values, negative 3, negative 2, negative 1, without skipping over 0, positive 1, positive 2, and positive 3. Okay? So we said 6. So don't go 2, 4, 6. That's incorrect. These can be empty, but you have to follow what rule? The bus seat rule. These are all empty seats. So we need 6. 1, 2, 3, 4, 5, 6. The value for M then is what? Is positive 2. It's pointing up. So what do we got? Positive 1/2. No. Only if you want to get it right, you'll put this. If you want to get it wrong, you can put 0.5. We want the fraction because that's what's associated. Now, you might think, that sounds really silly. Well, what about if we allow you to have some of them bad habits, and then 2 years from now, 3 years from now, you're in a college lecture hall, and would you, how many of you would feel comfortable asking questions at the college level when you're in class? Okay, all right, but otherwise, one of two things can happen. So where did you learn this from? And two, point 5 is not even a selection. I get it what you mean. It's kind of like saying, when we're looking at, for instance, oxygen, okay? That's not a numerical value. This sign is just telling you the charge, okay? That's what we're getting at. It has no value. It's just saying that it's the charge, not the value, the charge. Okay. Yes. Okay. Because sometimes it depends upon, I always got to think about that, which periodic table you're dealing with. Okay, so you came up with 7. So if you're looking at that, you have to add this in here. That's right. Because when you look at this, it says 57 to 71, you have to include lanthanum and actinium. So that's how, yes, you would get 7. So then that means that M should not be +2, it should be plus 3. It should have went in here, okay? Because some tables account for that, others do not. Yeah, this table does. I was glancing over at that one thinking, okay, that's 6th column. Nope, it's the 7th one. You are correct. Okay. Is there any other questions, or have you had enough fix of this for today? But very quickly, what we will establish, because some people like saying this word because it's so funny, on page 111, okay, it says the first rule shows the order in which electrons occupy orbitals according to the Afabu principle. Okay, it's better known as the slide rule. That's how I want you to associate that. It says an electron occupies the lowest energy orbital that can receive it, and that's why your slide rule is so important. Okay, and that's what they're trying to illustrate there in figure 16. It's just that it's upside down from your slide rule. Okay, so the Afabu principle then is your slide rule. Then when we talk about Hund's rule, okay, on page 112. Okay, we have the Pauli exclusion principle. We're not far enough along to establish that, but the third rule, this is halfway down on the top portion of page 112, it says the third rule requires placing as many unpaired electrons as possible in separate orbitals. Those separate orbitals are better known as your bus seats, okay? Okay, in separate orbitals in the same sub-level. In this way, electron to electron repulsion is minimized so that the electron arrangements have the lowest energy possible. According to Hund's rule, orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second electron. That's why if you have more than 7 here, if there was 8, all these empty seats are going to be filled first, then it's going to be paired with another one. So that's why it's better to say the bus seat rule than Hund's rule. You can say Hund's rule if you wanted. But I see the segment that I wanted to read yesterday. You can just listen to this, or you can look at the bottom of page 111. It'll be the last thing we do. Okay? It says, note the figure, for example, that the 4s sublevel is lower in energy than the 3D sublevel. Therefore, the 4s orbital is filled before any, okay? 4s orbital is filled before any electrons enter the 3D orbitals, okay? So, what's that telling you? What your slide rule? What comes first, 4s or 3D? 4s. So you would agree that you should always write this first, according to what we just read, correct? So if you are looking at these tables later on in this chapter, like for instance on page 118, they're just placing them in numerical order for convenience. But we just read that this has to come first. So why the author chooses to do that on page 118, I really don't know. But we want to remain consistent. This always comes first because it requires less energy to fill than the 3D. All right. At some point, we're going to start. I didn't know how long it would take, but two of the probably one's lesser known for chemistry than as opposed to physics, but the other one's very well known for chemistry, and that's Niels Bohr. Okay? When it comes to electrons in this quantum state, as we were talking about that yesterday, do these behave because of what we call electron entanglement, that they're infinitely attached? Or is it the spin, or what we call spooky action, like Albert Einstein had said? So that's a video that does hopefully what we feel a good job of explaining why these electrons behave the way they do. It's something that is probably much better explained to you than what I ever could. Okay? So we will be doing that the next few days. I didn't think we were going to get up to these quantum numbers yet, so we're kind of a little bit ahead of schedule. It says assign worksheet 1 tomorrow. I don't believe we will hand that out. Maybe it's not like I like giving out Friday assignments, but I don't collect them on Monday anyway, so it's not the end of the world, people. So just keep that in mind. That's where we're at and where we're going. So if you have any questions, find a classmate, find a senior. The organic students sitting here saying, I was good at that stuff. So I'm sure seniors would be more than willing to help you if you were to ask if you're having problems. You got these videos that you can look at, or you can come talk to myself. We'll pick up with this tomorrow.